हेलो।
हाँ जी।
आपने बैकग्राउंड में ऐसे कैसे ले आया?
मैंने वो
नाइस।
अच्छा लग रहा है।
हाँ एकदम।
हाँ बढ़िया है फिर। और टॉपिक में मेरे को इशू नहीं है, लेकिन वो है कि मैं लैब में बैठा हुआ हूँ, यहाँ नॉइज आएगा।
हाँ नॉइस आ रहा है।
नॉइज आ रहा है ना, इधर से नॉइज जाएगा तो बेटर रहेगा कि मैं प्रेस दूंगा एंड यू डू द टॉकिंग।
ओके हाँ।
नो इश्यूज ना। ठीक है, मैं म्यूट कर रहा हूँ अपने आप को। मैं जरूरत पड़ने पे ही बोलूंगा बिकॉज इधर नॉइस आएगी, मैं लैब में बैठा हुआ हूँ अपनी।
ठीक है।
तो मैं प्रेजेंट कर देता हूँ।
हाँ ओके फाइन।
आई होप कोई पैच नहीं नजर आ रहा ना।
नहीं 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 कुछ नहीं।
फिर ठीक है। फिर भी अगर जरूरत पड़े मैं बोल दूंगा, कोई दिक्कत नहीं है।
हाँ हाँ ओके नो प्रॉब्लम।
सवेरे जो मैं प्रेजेंट करा तो नीचे से वो हल्का सा कट रहा था, अभी मेरा तो नहीं कट रहा है ना।
नहीं, तुम्हारा नहीं है।
पूरा दिख रहा है ना, मंडे पूरा
हाँ
दिसंबर।
हाँ, मेरा वो टास्क बार आ रहा था, तो स्लाइड में क्लिक करना था, एक बार क्लिक करने से चला जाता नीचे। हाँ, आपका सही है।
तो ठीक है।
Good afternoon, sir. Hi, Akhil.
Good afternoon.
Hello, good afternoon. Hi Avinash, hi Jeet.
Yeah.
Nice to see you both.
Yeah, same here.
How are you doing?
We are doing fine.
Had lunch?
Ready, thank you.
Yes, sir.
You had your lunch?
Yeah.
Yeah.
Perfect. Yeah. Well, that makes sense why we are all so happy. Where are you
Happy
from?
because of this session.
Hey, great to know that. So where are you guys from?
Yeah, it was nice. We are PhD student at IIT Bombay.
Okay, so you're doing a PhD?
Yes, sir.
Yes.
Oh, great. You don't have to call me sir. You can call me Akhil. That's more than enough.
Yeah. Okay.
Yeah, for one, it makes me feel old. Two, I don't, I have not earned the title of sir yet. Great.
Yeah.
So, which area are you working on, Avinash ji?
I am working on.
Consensus building in the material system.
I'm sorry, I lost you there.
Consensus building in material system. So.
Oh, that's great.
And I am working on snake robots.
Oh, snake robots.
Yeah.
With the flexible material or junction of joints.
Junction of joints for now.
Oh, that's nice. Yeah, that has been one of the key areas that I was very intrigued when I was, learning about robotics. And yeah, it has its own beauty, right?
Yeah.
Yeah. I think a couple of people are trying to make it using this polymer kind of thingy, right? Which can be actuated by some sort of electric signals so that it can bend and twist and make it move forward.
Okay.
Quite nice. I'm quite excited. Do share something if you find
Okay, sure, sir. Yeah.
Great. So my research was in the area of adsorption process kinetics, or nowadays it is quite famous in the name of I'm not that old, so it's famous in the name of physics. What physics informed neural networks. So that's the broad area that I was working on. Yeah. Yeah, not so long ago, a few years only, but still it's nice to see so many beautiful new things coming out across in different areas. Quite nice. So I think Pranav and Shavik would be joining a little late.
Okay.
Yeah, luckily I'm on time this time around. So how is the conference going on in generic terms?
Fabulous. We had this morning session. There were 2 parallel sessions while MATLAB was going on. There was one parallel session going on IoT also.
Okay.
So after that IoT session, there was a talk by Naga Prema Raju from MATLAB only.
Right. Yeah.
I guess.
Yeah, Naga. I know.
So, yeah. And just before this session is to begin, there is a session going on by Professor John Legros from PhD.
Right.
On data-enabled predictive modeling.
Great. I wish I could attend others also, but somehow things don't work as planned when it comes to work. Right. So you're from which department? Both of you?
Electrical.
From electrical. Oh, nice.
Yeah. Control and computing groups is there. So we are both from control and computing group.
Oh, nice. So is Professor Sachin Patwardhan a part of this group?
No, Sachin Patwardhan is from chemical department.
Right.
And he is also an associate professor in SysCom, System and Control department.
Nice. So I have been there to IIT Bombay once for this technical fest is there, right? Azeotropy or something. So I was there once. It's a beautiful campus out there you have. It's very nice.
Yeah, you did it from IIT Madras, right?
Yeah.
Yeah, I visited there once for a faculty development program. There was so there I visited. Deers are there like cows in our campus.
Yeah. So you get deers, black bugs. I don't know what else.
Yeah.
Monkeys are the specialty there. So my faculties, professors used to joke sometimes that we got human monkeys and the normal monkeys. Don't know which one is more troublesome. Quite nice though. So when are you? Sorry, which year are you guys in? Final year or pre-final or what?
I am third year.
As you know, that PhD doesn't have any.
Right. But still, we try to figure it out in terms of this. Yeah.
I am in third year. I think Jit is in second year. Jit.
Okay.
Jit.
It's already second year. Already past 2 years.
Is it surprising?
Yeah.
You're a lockdown researcher, huh? So apparently they have names for people who joined during the COVID lockdown time, right? The COVID batch or something. It's like that's not a great name to put for people. But yeah, not being in the campus is one big loss for every single person, I guess.
Yes.
Especially for people who have experiments to be done.
Yeah, that I was about to say, like, since most of our works are simulation based, it affects us less than the people who have actual lab things to do.
Yeah. So my lab friends were still there. So they mentioned sometimes, that they had to do one experiment, which usually takes 15 minutes, but this time it took 6 months to get hands on everything. So many approvals and so many things are pending, right? Yeah. How's the situation there in general in Bombay? Are you guys in Bombay or someplace else?
Yeah. We are at Bombay. Situation here is now fine, much better, and also the new trait has come in, that Omicron.
Situation is better, but being in Mumbai,
I tend to call it
already flooded
OMG
with
strain.
cases.
So I call it a OMG strain. I don't know what else to
Yeah.
say. So the cases have come down, or is it still the same?
Now there are few
Cases
cases
have
of
definitely
yeah,
come
now
down, but as come to the other states or other major cities, if you see that still there is
Okay.
more cases than any other cities.
Yeah, makes sense. The only other state which would have more than Maharashtra right now would be Kerala.
Yeah.
Kerala is going evergreen and strong on that front, at least. So that is one area we would not want anybody to lead. Great, then I'll take a 2 minutes break. I'll grab a
okay, sir. Yeah,
bottle of
sure.
water and then get back.
Mhm. Hello, Avinash. I think we have to call
Huh?
our chair and another one, right? Another speaker. Do we have to call him?
Yeah, so I may call.
Can you send a text to him? Just a reminder to Sobit sir and Pranav sir.
Just a second. Can you repeat?
Can you just send a text or some sort of reminder to Sobit sir and Pranav sir?
Yeah, yeah. I'll just send it them the reminder.
Yeah.
Jit Kole and Avinash Dubey.
Hello,
How
sir.
are things?
Fine from our side.
Chalo, great, great. Both of you are looking very confident now. Thank you so much. I mean,
Thank
this
you.
is going flawlessly now. This is amazing, amazing.
Hi, Ajit.
Hello.
I'll make call to Dr. Savik because I don't think that his net is on. So I'll just make regular.
Hello, everyone. Hello, Pranav. Good afternoon.
Hi, good afternoon.
Good afternoon, everyone. I hope you all are doing good and had a wonderful lunch.
Good afternoon.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon.
Yeah.
Welcome back to the afternoon session.
Thank you. Welcome. How are things going in the conference?
Everything is going great.
Awesome.
Hi, Shavik. Good afternoon.
Hey, Akhil. Good
Good
afternoon.
afternoon, everyone. I hope everyone had a good lunch once again. So I have a belief that good learning happens in a full tummy.
Always true. This the lobby thing is pretty nice in Zoom. Seems.
Yeah, it's quite friendly.
Yeah, it feels like a conference.
Yeah, it'd be great to see everyone in person though.
Hello, everyone. So it's 3:30 now. So I am handing over the stage to Souvik sir to begin.
Sure, thanks. We can get started. Just one question to everybody, since it's kind of a continuation from what we did in the morning. Akhil was talking about a lot of nice, interesting concepts on reinforcement learning. How do we frame the policy, the environment, the reward? It's critical that sort of you understand how do we frame the problem for different type of problems. And he also showed like what we're going to cover in the afternoon session, kind of a trailer. So anybody is in the audience who was not there in the first session, you can put in the chat window again if needed, or also please feel free to unmute and say anything. During the event, also during the session, if you have any questions, please feel free to unmute and ask. Through the chat window, we can put some relevant links and answer your questions, share resources which you can read later on. Yeah, so if anybody was not there in the first half, I think what we can also do is we can share some similar type of recordings, or I mean, if this is, since this is recorded, we'll see this as well. But if you need resources, there are multiple reading materials and resources. We can share those things which you can go through later on. So let us know if something is there which you did not follow or you are not there. Yeah, I guess during, like Akhil ended with a question, like something for you to think about. We can hand over the stage again to Akhil and Pranav to take it from there. You can share any thoughts, any questions that came across while listening to other talks or while having lunch. Please feel free to let us know as well, and that can be taken up. So speaking of that, I think we can go ahead. Akhil, do you want to take it over?
Yep. Thank you, Shavik. Let me share my screen. And then we'll start from there. Okay. I hope my screen is visible to everyone.
Yes.
Perfect. Hey everyone. So So happy to see you all back, and I hope you are all, had a wonderful break and lunch, and the sessions have been quite well and nice till now. So just to give you a quick recap of what we did, let me walk you through, take 5 minutes and walk you through this particular, until we reached up over here. We talked about what are the different problem statements which are out there, which are quite different from the traditional ones that we see. We talked about what is our problem that we are trying to solve today, which is a biped robot trying to walk on a straight line. Then we talked about what traditional approaches are there and what alternative we are looking at, wherein we introduced reinforcement learning, wherein we equated reinforcement learning with an example of a puppy being trained by a lady. And we figured out what are the different entities that will help us frame an explanation or definition for reinforcement learning as a type of machine learning wherein an agent or a machine is trying to learn through trial and error interactions with the environment, right? And we try to define what is the difference between the different types of learning process that is out there: unsupervised, wherein we are looking for patterns; supervised, wherein we are trying to correlate these patterns with a defined output; and when there are interactions, and that is where we are learning on different aspects, we talk about reinforcement learning. Then we talked about an example of we talked about where deep learning comes into picture and what are the kind of problems where deep learning usually find its placement. Then we talked about an example to correlate between different entities of reinforcement learning with the pet training analogy. We talked about agent being the entity which learns to perform different tasks that we require through trial and error. We talked about observations that is being made on the environment and the actions taken on the environment, actions being done on the environment, and how the policy is the mapping between observations or states and actions, and how the environment actually gives a reward, which is how the policy can be updated using a reinforcement learning algorithm, right? And to put this all into perspective, we took an example of self-driving car, and we talked about what different entities would be in terms of a self-driving car. With that said, we went into when do you call a policy to be trained, and how the definition of trained is very subjective to each person in the requirement. And post training, you can actually deploy policy on its own so that it is able to take proper actions for a given observation, right? And then we talked about what are the parallels between control systems and reinforcement learning, and we identified what different things would be when it comes to control system and reinforcement learning. Then we talked about a problem statement wherein we wanted to navigate a red circle in a grid world to reach a blue square with minimum number of steps, wherein we introduced the reinforcement learning workflow as kind of a standard workflow which you have to follow in case you're working with reinforcement learning. And then we talked about how to set up the reinforcement learning workflow entities for our problem of a 5x5 grid. We talked about how to decide on a reward. We decided on rewards based on what was our requirement, that is the shortest step with maximum reward to reach the blue square, right? And we talked about how the environment has been set up, and it is up to us to, and our flexibility is there to set up the reward in the environment. Then we talked about what might be the problem case when you start with this, because we do not know where the red circle is starting from. Then we talked about how the red circle does not know where to go, but initially during trial and error, it finds out certain good steps and kind of remembers that. We created a Q table. We defined what reward is, what value is, and what Q value is. So reward was something which was instantaneous, feedback given by the environment. Value was cumulative reward over a time period of, state transitions. Then there was Q value, which was based on what actions led to those particular values, right? And then we created something known as Q table, which was able to give us a solution which was quite generic, as we could see in the next slide. We saw that a generic solution may look something like this. So we understood that in this particular problem, we were not actually working with the policy, but we were identifying the values first. And once we identified these values, then we extracted a policy out of this, right? And then we scaled up the problem. We were like, okay, now we were working with 5x5 grid world. What if it is a larger grid world? And if people believe that this particular grid world, it's easy to create a table, then we talked about, okay, what if we scale it up further? What if we are talking about a simple robot arm manipulator, which has 6 joints in there, which have almost 3 trillion states? That becomes a little bit, I would rather say not little bit, but a lot difficult. So we left our first portion with a small question to think big, which is what can be an alternative to ensure that we are even able to work with reinforcement learning for such a big system with so many possible states, right? And I hope you have had time to think about it. So can you please share your observations in the chat window? For those who could not attend the first session, I hope this gave you a quick starter on what different parts and entities are. Please do not worry. At any point of time, something is not clear to you, please let me know. Otherwise, we'll also be sharing material which you can refer to once the session is over. And you can also get a complete sense of what we actually talked about. Okay. So everyone, so what do you think can be an alternative to actually creating a table of states, to identify what possible actions or, what possible combination of actions we need to take? What do you think is an alternative? Remember, I did give you a hint on what might be a possible solution to this. So I want everyone to participate with me during the session, just like the way you did amazingly in the first half. Drop in your thoughts in the chat window. There isn't any right or wrong answers to this, right? Okay, Satvik mentions deep learning. What exactly do you mean by deep learning, Satvik, out here? Are you referring to that we should use neural networks? Everyone, please participate. Whatever you believe, please put it up. You mean to say deep neural networks? Okay. You mean to say we should use DNNs? Great. Okay. Any other answers? Any other guesses? Please do not mind answering. Whatever comes to your mind is an answer good enough for us all to know about, right? Great. So let's not dwell much, I guess. So we do have a small frozen start, but no worries. I'm pretty sure. Yeah, transfer learning would also be possible. Okay, great. So I guess the gist of what everyone wants to say or maybe thinking about is, we try to, instead of putting out a table, we try to approximate it or predict it using a function, correct? That can be a possibility, right? So the whole idea is, when it comes to many states, typically what works quite well for us is, let me just change my pen mode. What may work good for us is basically deep neural networks, right? So the whole idea is neural networks are kind of like a, it in a generic sense can be said as a, universal function, universal function kind of mapping, right? Wherein by altering the weights and the, the transfer functions, etc., you can actually tune this neural network to kind of predict most of the things that you want to work with, right? So that's where deep learning will come into picture. So the whole idea is, you do not have to use deep learning everywhere. The thing is, it's more like, trying to kill a mosquito using a missile, which we do not want to do, right? So only when things become too complicated or non-linear, and you believe it has more perks to use a black box system like a deep neural network to work with in this particular case, that you want to work with this. Otherwise, it would be always suitable to have some sort of functional form or a, tabular form, which can give you an idea of what is happening or what are the parameters that are affecting the decisions that are being made, right? Great. So that brings us to the different types of policies that we may have. So we have seen a kind of lookup table in terms of Q table, right? We have talked about it can be polynomial functions also, because they are also there. And it can be deep neural networks too, right? Now comes the agent, because at the end of the day, any policy is as good as the way that we train it or update it so that it is able to perform the required actions for given states or observations, right? So when we talk about the agents, the first agent that comes to mind is 007, but that's not the kind of agent we are talking about. We are going to talk a little bit more about the kind of agents in reinforcement learning, which is going to help us update our policy to ensure that our policy is able to take good actions, which would be good, better rewarding at every step for a given observation or state, right? Let's talk about different types of such agents out there which are helping to get these, get the policies updated in a proper format. So let's talk about how do we go about training these. So there are three different types of RL algorithms. There are a few others, but I'm going to focus on three major ones, which is value-based, policy-based, and actor-critic. Okay, so let's talk a little bit on what value-based would be. So to get to value-based, let's take a minute out here and try to understand and think, right? What exactly did we do in terms of grid world and what is happening out here? So take a minute, let's rack our brains a little bit and see what we come up with, right? Share your observations on what you see out here. What do you think is happening? Like take a look at the chat window to see if there is any question. Can we constrain the grid space using the physical model dynamics? Well, that's an approach that you would be very interesting. But the thing is, how would you model it, right? So it will be highly dependent on model. Right. So what do you think is happening out here, everyone? Or what do you think we did out here in our grid world? And please do not mind, you already know whatever we are trying to say. The only thing is we are trying to put it in formal terms so that we are in the same page when we are going to implement this for our biped robot. So any quick guesses? What did we do up here in this particular scenario? How did we end up with this particular policy that you can see? Okay, we have an answer. On the left, it seems it's kind of like a graph search wherein nodes are connected based on adjacent nodes that can be reached from a given node. Okay. Okay, and how is the connection being made? Or how is the path being selected? Based on, oh, sorry. Yeah, my keyboard actually played a trick. Based on minimum value. Okay. So are we actually highlighting a path with minimum value out here? Are you sure? Certain on that? Yeah, based on cost required to traverse, that's absolutely true. So the thing is, either if we are looking for a path with minimum value, or if we consider these values to be rewards, it would be a path with maximum reward, correct? The whole idea is, in either of the cases, our focus is not to kind of map what actions to take for a given state, right? What action should I take from here? What my focus is, what possible rewards I can get from this state, maximum possible reward, right? So we are very greedy right now, right? We are greedy and we are trying to look at what is the maximum reward I can get. It says, okay, this way I can get maximum reward. Here we are taking and we are understanding, okay, this way I can get maximum reward, right? The whole idea is the policy, which is a mapping between what actions needed to be taken at a particular state, is not our focus. Our focus is on identifying at whichever state we are, what is the reward we are going to get, cumulative reward, or cumulative reward is something we call as value. What is the value that we can get from any state transition, right? If we transit from here to here, what is the possible value that we can get? Because just to keep in mind, initially we do not know what the rewards are, right? The agent does not know what rewards it will get for any particular transition, right? In this case, it does not know what rewards it will get for moving from one square to another square. So what it is trying to do is, it's trying to identify, if I go from state 1 to state 2, what might be the possible value I can get, or possible cumulative reward I can get. It's trying to estimate that, correct? And now based on that, once we have identified all the possible state values in terms of our Q table, once we had that information, we finally came up with, okay, so this is the path we should take, or this is the direction we should move if we are in this state. This is the direction we should move if we are in this state. So the policy, that is the mapping between the states and the actions, is derived from the value, or the value function that we identified. Is that clear to everyone? So the whole idea is, we identified what would be the estimated cumulative reward that we can get for any state transition going from one state to another, right? And based on that, once we were able to estimate that accurately, we've ended up finding out the policy for us. Okay, so policy is an afterthought. It's kind of like a derived thing. So there was a question on policy and off policy today morning. So basically, if the actions are taken based on what policy suggests, that is on policy. That means you're taking actions based on what the policy is trying to tell you. Policy is also a function. We'll talk about it as we go forward. So policy would be trying to predict, okay, this action would lead to this reward, so you should take this action, right? But if the actions are being taken not because of policy, but because of the value itself, right? Because of the value function, then that becomes value based, right? That means off policy. We are not working with respect to policy, but we are going to work with respect to values, and then finally we will be extracting the policy out of this value. Now, a quick question, is this clear to everyone? Because if this is clear, rest everything is straightforward.
Can you explain what are the nodes in this graph?
Are you talking about the left one?
Yes.
Right. So let's assume that this is a world of nodes. Okay. And the objective is to maximize, reach this particular blue node with maximum reward. Let's assume. Okay. So whatever limb values you can see, like 5, 4, 8, 12, 5, 7, 11, 10, 9, 6, these are all rewards, potential rewards it can get, right? Initially, when you are at 0, it is not aware of any of such reward values, right? So what it will do is, let me, restart the animation that we have up over here. Initially, it does not know. It traversed to the state, it found 5. It traversed to the state, it found 4. It traversed to the state, it found 8. Then it traversed to, through 4 to a different limb, right? For example, if it is trying to find the path with least or minimum, sum of these values, let's say it can be anything, right? Then it identified, okay, going to 4 is the best one. Then going to this this particular limb is better from 4, irrespective of this. Then from here to here, it is able to go from this limb, right? So what I want to highlight up over here is, the decision is not based on what action to take. The decision is based on what value you will get.
Is it like a star path graph search, like an A-star algorithm?
We can, it is similar. It is similar, not identical, it is similar, but you get the gist of what this is doing, right?
Yes.
The gist is, we are trying to identify which path will give you the required reward, whatever it is, whether it is minimizing the values or maximizing the values, that is different. But it wants to kind of perform a task for a given objective, but the task or whatever actions it is taking is based on the values it is going to get. That's it. It's trying to estimate that and get it. So just to make it a little bit more simpler, for example, So let's say, the previous one, we had a table, remember?
Yes.
We had a table of states, left, right, up, down, and we had, Q values, correct? So now the beauty is, let's call it as Q for left, Q for right, Q for up, Q for down, right? And let's not use this. So if I am at state 1, so let's say some value 0.9 or 0.2, 0.4, 0.8. I'm just giving you just random some values, okay? So if that is the case, you will see if you are at state 1, the direction you should go is 0.9, right? This particular left direction. So the whole idea is which direction you should go on is decided based on the Q value that you estimated, correct? And the policy is what? Policy is basically, if you're in a state, what action should be taken, correct? What are we doing up over here? If you are in a state, what Q value you will get, right? And once you have identified this, from that you are extracting this. Is it clear now? Is it better?
Yes, thank you.
Yeah, great.
Akhil, there are 2 more questions in the chat if you can have a look at it.
Okay, yeah, sure. Thank you, Pranav. Won't the value of a state depend on the current policy? A particular state cannot have a unique value then. Right. The beauty is right now we do not know anything about the policy, right? As like initially we do not know anything about the policy. You're creating the policy based on what is the cumulative reward you're going to get, cumulative Q values you're going to get, right? So yes, a particular state cannot have a unique value then. Absolutely. A particular state may not have a unique Q value because the Q values would be, it's going to depend on what was the previous state it transitioned from, right? So it's kind of like estimated future values that you can get. Yes, you're absolutely right, Ronak, over there. Second question is, Akhil, this process of finding the optimal policy is, as I am getting, based on if we know the environment completely, where the agent is operating. What if we have limited information? That's a beautiful question. Yes, in this particular case, we are dependent on the information of the, or the knowledge of the environment. But ideally speaking, if you have enough information of the environment and you can identify rewards that the environment can give you for taking up any state transition or actions, then you would be able to make a good reinforcement learning model. But the problem is that may or may not work in all the situations because you may not be able to verify it for edge cases or any other any other wider use cases. For example, let's assume that you had certain data, limited amount of data that you had with respect to a road environment wherein you wanted to train your car, self-driving car. Now based on that, you have created a reinforcement learning model, which is a reinforcement learning agent, which is quite nice, right? Which works for that data. Now the thing is, what if that data does not contain any critical conditions? For example, what if there is an extreme rainy weather and water is flooding? So that kind of a thing is something that the policy is not encountered, and you cannot actually simulate that, right? Because your environment is not there. So that time, testing these for edge cases become a little difficult. So there are 2 types of reinforcement learning that you might be, if you're not aware of, let me let you know. One is model based, one is model based and model free, right? So when we are dependent on the environment, or we are dependent on the model to give us the required information and direct our training, that's a model based one. So we have model free ones also, right? I hope that answers both your questions, Ronak and Soumyadeep. Is this idea implemented to multi-agent tracking? Arnab, can you please elaborate what you want to say in this? So a subset of the environment that is relevant to the current problem or a class of problem to which our problem is one of that class. I'm sorry, let me read this once again. So a subset of environment that is relevant to the current problem, okay, or a class of problem to which our problem. Yeah. Yep, absolutely. So you would have figured out by now that having an environment can be very rewarding. So that means not having an environment can be a little tricky too, right? But yes, either of the ways you can still train an agent, but the quality and the purpose would be quite different. Yeah, please go ahead.
Okay, okay, I understood. I got your point.
Great, thank you so much. Any other questions or doubts?
Hello.
Yes, please go ahead.
Yeah, what I wanted to ask is, if we are finding the value of a state, we will need to find the rewards from going from that state onwards to the final state, right? So we'll need to have a policy which tells us which path we are following.
Absolutely. So that is the policy that we want to extract, but that is not the policy which is guiding us to go that way in the beginning, if you notice. So let me put it in this way. When you had this table, right? Let me kind of draw this again. When you had this table, correct? So let's say we begin from this particular thing. QL, QR, Q up, Q down, right? Let's say we begin from this. Initially, you're here, everything is 0, 0, 0, and you have this all 29 tables.
Right.
29 states, correct?
Yes.
Now, first iteration, let's say you started from this particular 1, 1 or something. Okay. You started from 1, 1, let's say from here. So what it does is it takes first transition, right?
Yes.
So it takes first transition, it gets some sort of reward.
Okay.
Right? It can take any of the transitions. It's random. It's a random thingy, right?
Yes.
It took one, transition and it got some reward. And based on that, you can compute the Q value, correct?
Yes.
So the updated table would have some sort of Q values, let's say 0.2, 0.5, 0.1, 0.5, whatever it is, right? Let it be randomized. Now what you do is, okay, now you got the Q value. Now second iteration comes up, right?
Yes.
Now, based on this particular Q value, now it is going to take another trial and error step.
Okay.
Okay, it's trying to predict, okay, if I go in this particular direction, what would be the reward or what would be the value I can get? Okay.
Yes, yes.
Now, again, it got some reward. It then updated its own table, right? So you understand, every trial, the table is getting updated.
Right.
Right?
Yeah.
So the thing is, the next time when it comes to state 1, 1, there is more possibility that it will go in the direction that it has already explored, right? Which gives it the maximum Q value. But that is a greedy exploration, correct?
Yes.
So that's why we always keep another set of, a parameter which we call as whether you want to do a greedy exploration or what fraction should be exploratory, right? Like it should be explorer or navigate. There is a word, I'm totally forgetting that word right now. It's basically either you want to be greedy or you want to be an explorer. So greedy is going towards a direction which you know will give you the maximum reward or maximum Q value. And explorer is randomly taking some different step so that you can explore the world a little bit more. For example, in this particular state, there are two possible paths it can take, correct? It can go right or it can go up. If it started with up and we were only working with greedy learning process, then it will only go in this direction. It would have never explored this direction. Get me?
Like exploration versus exploitation. Right?
Oh yes, that's the correct word. Thank you so much, Shavik. So we are trying to, have a balance between both. I hope this makes sense to everyone. Now it's clear.
Yes, thanks.
Right. So basically, we do not have a policy which is guiding us to go in direction. We are trying to take some random steps, identify what the Q values are. Then based on that, we are going to make our policy which will guide us. Okay. So that's value-based method. So you would have figured out a couple of things already, that this process will require us to keep such a big chunk of information with us all the time in the memory and keep on updating it every time you make a step or action, you take an action or a step. right? And then post that you will be able to derive a policy. Second thing is, if you have too many states, you would have guessed that the amount of memory and the computation and the updation would be quite large, right? And the computational efficiency will come down. And another thing you would have understood is the action space, and this action space is quite discrete in this. What if we have continuous action space? This becomes tedious, right? It's nearly not possible for us to have all the possible combinations out here. So you get the problems of working on a value-based set of system, right? Though it is very advantageous when we have some system which is small enough, trivial enough, with a simpler set of action spaces and etc. Right? I hope this gives an idea of what we are dealing with right now. Great. So let me now move ahead. So the whole idea that we just encountered and we just figured out is it's typically good to work with a value-based algorithm when you have a small, finite, discrete action space. And otherwise it will become very much unwieldy, to be very honest, right? And we have to run simulations again and again to identify what would happen no matter where we start from, what state we are in. So identify what state we should go to, right? What action we should take. And policy is not the focus for us. So if you put this agent to actually go to any other grid world, it will not work, right? Because it is not focused on what actions to take. It is focused on what value it was getting if it was transitioning from state 1 to state 2, which is highly localized to this grid world only, right? If you change anything in this grid world, the Q table will not be working now, right? Because the Q values would be totally different now. So I hope that makes sense to you. So if there are any questions as you come along, please keep on asking these questions. Thank you so much for being interactive. Keep it up.
Hello, sir.
Yes, please go ahead.
Sir, I'm Arnab. I'm asking about that. Is this idea is implemented to multi-agent based tracking? Sir, you have mentioned a target of that blue square. It is positioned on the 5+5 position.
Right.
Sir, and you started the problem with a single red ball which is chasing this blue ball.
I'm sorry. Are you talking about this one?
Yes, sir. The problem that at first you have mentioned that that we have to find a path between the red ball and this blue one.
Correct.
5+5 position. Sir,
Correct.
I'm asking about if I assume a scenario where there will be multiple red balls in this grid.
Right.
Now they want to chase that blue ball.
Okay.
In that case, sir, can it possible to implement this same grid idea as this nodal graph theory with using this one? It is possible to implement that thing, sir. I just want to know, is it possible or not?
Sure. So let me reiterate your question so that everybody is clear, and you also let me know if my understanding of the problem is right. So what Arnab is trying to say is, instead of having one red ball or red circle, we have multiple red circles which are trying to reach this particular blue square. Right? Right, Arnab?
Yes, sir. Yes, sir.
Right.
Yes, sir.
And is it possible for us to train the other red circles also in such a similar format? Right? So that becomes a multi-agent problem because our red circle is one agent and we have multiple agents now. For this 5x5 grid world, can we take same approach? Yes, why not? But you will have to put certain constraints out there. Can the red balls overlap each other on the same position? If that happens, what happens, right? So there are many, many different things. So like it can be like a game of Ludo also, if you take a look at it, right? So what happens if two different circles come to the same spot? So these kind of this is very brilliant thought that you had out there. Yeah, this is something that can be realistically possible. Because this grid world is very small, you can actually run with this Q table.
Okay.
Arnab, did that answer your question?
Okay. Yes, sir. Yes.
Right. But yes, the process would have a slight variation because there would be interaction between the agents itself, right? So if there is interaction with the agent, what would happen? Are you assuming the agents to be independent or not? Whether that interaction is going to create some sort of, a reward or not. So these are kind of considerations I'll leave you with. So the whole idea is, it is according to what we intuitively understand about a problem, or what is the intuitive understanding of, intuitive way of us to figure out what can we do in this problem statement, and putting that in terms of code, right? We have not yet reached the position of putting things in the code yet. We are only qualitatively analyzing right now, so that by the time when we reach to the implementation point, we have a very strong understanding of what direction to take. Okay, great. By now you would have figured out that the value-based approach is quite powerful, but it has its own shortcomings, right? What if I'm working with another problem? Is there any other approach? So that's where the policy-based approach comes into picture, right? Before that, let me give you a slight mathematical background on value-based approach. So I talked about Q-value updation, right? So Q-value updation happens based on Bellman equation quite famously. This is a dynamic programming, formula, wherein you're trying to estimate based on what was the previous state and what is the current state and what you're going to get, right? So you're trying to estimate the new Q value, and based on that, you're trying to tune certain parameters. Out here, a couple of things that I would want you to take a highlight on. The alpha value out here is kind of like a learning rate parameter. The gamma value is basically a reducing discount parameter. So sometimes what happens is, if your process is taking too many episodes or too many steps, not episodes, too many steps, then what happens is you do not want the reward to be, very, very much late coming. You want it to be quick. So gamma is a factor which kind of reduces the effect of the values which are coming later. So gamma can be 0.9. 0.9 means 0.9 this time, 0.9 into 0.9 next time, 0.9 into 0.9 into 0.9 next time. So that's a multiplier, kind of, right? Reducing multiplier. So that will keep your rewards in a finite scope, so that you are not running around, right? So the thing is, I have till now talked about problems where there are episodes, right? There is a definite end state. For example, in the previous, when we were talking about the grid world, we said that there is a definite end state, which is the blue circle, blue square, or there is a definite end state, which is, you should not get a reward value of, less than or less than minus 30 or something. So that's the whole idea. But there are certain cases where you may have infinite, episode is infinitely long. You cannot actually divide that into episodic nature, like stock market, for example. In that, you will have to discount. You have to use a discount factor so that your reward, when it kind of saturates down, you have a convergence, and you know where to end it. You know where to end the training process itself. Otherwise, it will be never ending, right? It's an infinite loop, and you don't want an infinite loop to happen. I hope that gives you clarity. What will happen if gamma is 0? Very good question. So I think your Q value will be only based on instantaneous reward that you're getting, right? This is the instantaneous reward that you're getting, and that's it. And that would not be ideally a cumulative value. It will be only focusing on what happens then and there. I hope that answers your question. Very interesting question. So there is another one model that you may be interested in, which is known as SARSA, right? State, action, reward, action, state, method. If you're interested, I'll share some, material for that also. Great. So this kind of equation, or Bellman equation, is quite, quite popular in terms of Q learning, deep Q learning, deep deterministic policy gradient, and many other algorithms that you would popularly hear when you talk about reinforcement learning algorithms. Okay. Great. Well, Amol, typical value of alpha will depend on the kind of problem state that you're working with. So there is no one size which fits all kind of approach out here, right? Great. Okay. So let's move ahead. I think we have spent quite some time here. So policy. So as I mentioned, the next set of algorithm or training regime that we can talk about is policy, wherein there is a mapping between observations and actions, right? It's a functional mapping. So what it is going to tell is, okay, if this is the current state of, that my agent is in, what actions should I take, which would give me good cumulative reward? Okay. And this function definitely has certain parameters which can be tuned in order to make the function mapping quite well, right? So in terms of a deep neural network, the parameters would be like the weights of the neural network, right? Now the problem in this, or now the advantage in this is, you are trying to kind of estimate what is the kind of correlation between actions and observations, which is desirable by the environment, which is desired by the system in the process itself, right? It's quite powerful, but the point is, in order for you to reach these parameters which can actually map and predict actions in an effective and correct manner, that will take a lot of iteration, right? So the process actually goes on like this. Kind of initially execute the policy. Let's say if the policy is a neural network, you execute the neural networks to the random weights, you collect the rewards. Now based on the rewards, what you try to do is update your policy parameters, right? Then you try to execute a different set of action, or for a different set of observation, you try to execute the updated policy. Then again you collect the rewards, try to figure out what's happening, and then update the values of the policy, right? So the whole idea is, this is kind of like an optimization workflow that you would have quite often seen, right? Like in your curve fitting, you would have seen you're trying to estimate the parameters. Something similar, the only difference is you're trying to estimate a policy which would give maximum of the total expected reward, right? That's what we want. So you could have guessed that there are many trials and samples required in order to get to this, and the algorithm that actually works behind identifying these parameters is very important. Usually gradient based methods, gradient ascent method is something that we deploy, but there are many more people who are working with some global optimization algorithms, like genetic algorithm, to speeden up the process as much as possible, but an ensemble of GA with other localized searches are there. Okay. Now, why I said that? Because usually when you're working with gradient based algorithms, there is a high possibility that your process of optimization actually get saddled out in one of these values, right? Some local optima, it will get stuck up there, and it will not be able to identify a global maximum. You get the whole idea, right? So it is able to identify a local maxima out here, and it is not able to identify the global maxima. So in that case, you are missing out on something very important, right? So you have to be very careful with the kind of parameters that you're putting for the algorithm itself, like the learning parameter. So there are so many hyperparameters that you have to take care of, right? Great. So I think this covers everything in terms of policy based. Any questions on policy based? Is this clear to everyone? So let me take a pause till now. Till now, whatever we have discussed, how clear is it for you? On a scale of 1 to 10, can you tell me in the chat window how clear is it? 10 being it's completely clear, 0 being it is not at all clear. So can you tell me in the chat window how clear things are for you? It will help me to kind of reiterate certain factors, because the next part that we are going to talk about is going to be very important. Okay, Shrikant, 5. Okay, great. Everyone, I please request you all to drop in your, what is the level of clarity that you have with respect to RL right now? Okay. 5, 3, 6. Great. I believe 5 and above is something that is quite nice, everyone. Arnab, please do let me know if there is anything that is not clear to you, because we hope everybody to be above 5 and 5 and above. Shrikant, even you, if there are any questions or anything that is not clear, please do let me know. Everyone else, thank you so much for sharing your Sharing your pointers. Great. Great. So let me reiterate this once before we go into our actor and critic method. Value based, we are focused on what is the value that we can expect in any progressive state, next state. We are trying to estimate what is the Q value that we can get in the next or the next state based on what is the current state. Correct? What is the current reward that we got from the current state? What did we estimate in the previous state, and what can be the value in the next state? And based on this, we try to identify a mapping between observation states and actions. That is the policy. We try to identify the policy based on the final Q values that we get. Okay. On the contrary, in policy based, we are directly trying to find a function or a mapping between actions and observations by tuning certain parameters of the function. We try to get this so that we are getting maximum cumulative reward. Okay. And the process is actually quite exhaustive with respect to the number of simulation or executions required. And we have to identify certain parameters to ensure that we are not getting stuck in local optimal points, but rather we are having we are able to achieve a global maximum policy or optimal policy. Okay. With that in mind, let's move ahead. Now, we have seen problems in both these cases, right? In policy based and value based. Now, actor and critic method is actually there, which is trying to address to these problems. Okay. People brilliantly identified that, hey, why are we talking only about one? Why can't we have a combo of both? So that's where actor and critic method came into being. So what we do up over here is we have observed that most of the cases that we are going to work with are going to be complex. So I'm going to talk in terms of neural networks, because that's what we default to when we have some complex situations to work with typically, right? So what we do in an actor critic method is you have two neural networks, the actor and the critic, right? Which are simultaneously tuned. The actor is something which is trying to identify what actions to take at any state. Okay. What should I take? What action should I take if I'm here? Right? And critic is something which is trying to predict or estimate what is the value I can get for a given action. Okay. So what critic does is it kind of identifies, okay, this is the current state. This is the current action that has been taken by the actor. I predict that, okay, this is going to be the value or the reward that I'm going to get. Now, based on that information, it is going to critic or guide our actor's performance. Okay. The choices that the actor makes will be guided by the critic itself. Okay. Now, just let's take a deeper dive into this. So out here we have actor, which is trying to choose an action. Then it will apply that action onto the environment. Then the environment will give some reward. Correct? That's the whole idea. This is typically what the policy does for us. Correct? So actor can be equated similar to a policy. Okay. Now what happens is the critic is going to use the observation that is coming from the environment. It is going to use the action that has been taken by the actor and then try to predict what is the reward value. Okay. This much is clear to everyone, I hope. Now, the prediction of the critic, that is the reward value, is compared to the actual reward that the environment gives, right? Because the environment is going to give you the actual reward and it needs to be equivalent, or your predicted value by the critic needs to be equivalent to the reward value, correct? When there is an error, when it is not comparable to each other, there will be an error, correct? Now, what critic does is the critic actually updates itself based on the error. It's kind of like fitting your curve. If there is an error, you try to tune the parameters so that your error is reduced, correct? And that's the way the critic is going to update itself and make itself better at predicting what would be the future values. Okay. Now, before I go ahead, is this clear? Any questions on this? So to give you an analogous example, for example, let's assume, me, Shavik, and Pranav are in a classroom. Okay. And there is a question on the board. Shouvik is asking us a question, and I am actor and Pranav is the critic. Okay. Now, based on the question that is on the board that Shouvik has asked, I take some action. I give some answer. Let's say option A. Now, what Pranav is going to do is, he is going to observe the question on the board. He is going to observe the answer that I have given and try to predict whether it is right or wrong. Right? Now, Pranav predicted that the answer that I have given is wrong and I'm going to get scolding. Right? Now, what happens is, Shouvik will give us some correct answer, right? Shouvik is going to evaluate my answer and say if it is right or wrong. Let's assume Shouvik said it is the right answer. That means whatever Pranav predicted, that my action is going to lead to scolding or something, that is wrong, correct? So that means there is an error between what Pranav predicted and what actually happened. So what happens is, Pranav is going to get an idea of this, right? He's going to say, okay, that means there is something wrong with my understanding of the problem. So he tries to educate himself, and so that the next time when he predicts, it is right, correct? So that the error that he's making in prediction is less. Is that clear to everyone now? What does a critic do? Okay. Now comes the actor. Now the whole idea is, we know about how the critic is improving itself, how Pranav improved, his own predictability. But now the point is, why do I need to improve him, and how is the actor getting any better out of this? Because it is the actor who is going to make all the actions, right? But how is it getting better? So for that, what happens is, the actor plays a very interesting role. Actor is not at all aware of what Shauvik's, what actual value the environment is going to give. In the case of Shouvik, me and Pranav, I am not aware of what was the actual answer. I'm not aware of that. Okay, I just gave the answer, submitted it, and just went away. I only talked to Pranav and I went away because Shouvik was not in the class. Okay, let's assume. When the time of the submission came, Shouvik was not in the class. I would get the result later on only, but I only talked to Pranav, right? We discussed right after the exam with our friends. So what Pranav tells me, or what value the critic gives, is something the actor believes is the ultimate truth. Okay, I'm going to believe Pranav 100%, saying that whatever he is saying, that is the ultimate truth, and based on that, I'm going to study better and make myself better, so that next time Pranav is going to give me good response or good value, right? And that's exactly how the actor becomes better. So actor's betterment depends on the value that is predicted or estimated by critic, right? So in this case, my performance would depend on how good or bad the value of the suggestions given by Pranav is, right? So you got the whole idea. So I am never ever directly in contact with the environment. That is Shouvik in our case, right? So in that way, what happens is, if the actor has to make good actions, or it has to take good actions, the critic should be predicting the value in a good format. Only then the actor's prediction will be better. So you understand why we are saying it is a simultaneous tuning of actor and critic, right? So both actor and critic should simultaneously become better, so that the critic is better at getting correct reward values, and based on that correct reward values, actor will also become better, right? Right. The critic is updated, during every episode. It is not only updated every, after an episode. It can be continuously updated, or it can be updated in each transition. Yes. Any of the following is possible based on what is the kind of situation that you're working with, right? Usually it happens during each state transition or actions, or a batch of state transitions and actions. Depends. So before I go ahead, is this clear? Yeah, please ask the question.
Yeah, my question was basically like, if it is like every action that is taken continuously, then local rewards can be negative, but like some of the actions which are negative locally might be good, like overall, like to reach the final state. That is the blue square in a way.
Right.
So is it like every episode, or like locally?
So again, the thing is, what is the process itself? Are we looking at an overall episodic update? Does your system requires an episodic update, right? Or your system requires something which is based on every state transition itself, right? So the whole idea is, what is your objective? Do you want to identify what happens during every state that is possible there? Or are you trying to estimate on an overall sense whether the overall reward that you're getting is actually correct or not? Or is it actually maximum or not? So it depends on your problem statement, to be very honest, Anuj. I don't know if I'm actually able to relate and understand the problem, the question that you mentioned just now. Is it the same?
No, I think I understand it. I think here the goal is not to reach a particular state, but to create a reward space and a
Correct. So what we are trying to do is, this is kind of creating a Q value. If you notice, this is kind of creating the Q value table that we saw in the first problem, right? For every state and every action that you take, what was the value that you got? Correct?
Yes.
Whereas here it is more like policy, because for every observation or state, it is taking an action.
Yes,
I
understand that. Yeah. Thank you.
Great. Thank you. So now to move ahead. So what happens is, actor and critic method actually kind of combines best of both worlds. So we actually get, amazing results. We are able to work with, we are able to update policies, and we are working with policies. So these are quite generic when it comes to environments. We can work with continuous action spaces also, right? And these are more sample efficient. We don't need as many samples as policy based, but not as less as value based too, right? So we are kind of striking the balance out there. And it can also learn stochastic policy. So what does stochastic policy means? So the policy can either say you can go up, down, left, right, or it can say there is a 50% probability you should go up, 20% probability you should go right, 20% probability you should go left, 5% down, or something of that sort, right? So that's a stochastic policy, wherein there is a probability distribution amongst the most probable actions you should take. I hope that is clear to everyone. Right, now let's actually bring in our actual problem statement at hand. So first of all, these are a couple of recordings that I want to show you just to introduce you to the environment itself. I have embedded them in this presentation, so I will probably share this presentation with you. But before that, let me open up Simulink and actually show you what exactly this looks like. Okay. So let me reshare my screen. Do let me know once you're able to see my screen completely. Are you able to see my MATLAB screen?
Yes, Akhil.
Perfect. Thank you, Pranav. So now the whole idea is, now we are talking about implementing whatever we have learned so as to create our biped robot which can walk, correct? So this is MATLAB. I hope you're familiar with this. If not, this is how the MATLAB, when you open it up, it looks like. There are three important aspects that we have to take a look at: current folder, command window, and workspace. So current folder is basically the directory where you are in right now with all the files that you can work with. Workspace kind of contains all the variables that you have declared. So I had declared certain variables, so it is there. If I clear it, it will get cleared. And you would have guessed by my current action, you would have guessed what clear does, right? So let me close this first. I'll tell you what this is, okay? Let me close that first. So command window is basically an area wherein you can put in all your commands and then execute it, MATLAB commands, right? Now, so these are the files for the biped robot. I will be sharing this with you all so that you can go back and try it out on your own. I think more than hands-on, this is something that I would want you to observe first, and then you can try it at your end. Okay. So in MATLAB, in order for us to work with big projects or something, I usually prefer something known as MATLAB project, which is kind of like putting all the files together. So I've created a project for you. You can open it up, right? It helps me to version and kind of ensure that everything is working properly and on. So what I did is, in MATLAB, there is another functionality which is known as Simulink, which is a dynamic system simulation environment, which is based on block diagrams. Just to give you a sense of what it does, let me open up an example for you. So let's assume that I'm trying to simulate the dynamics of a ball bouncing off a surface, right? So what you see out here is the equation of that particular ball bouncing off the surface, right? It's an equation for that, and based on that equation, if I'm integrating that equation twice, I will get my velocity and the position, right? So if you notice, I'm not writing any equations out here, rather I'm using certain block diagram to kind of create this equation, right? And when I run this block diagram, that is executing this block diagram, what Simulink does is it numerically integrates these equations, or solves these equations at the back end and tries to give us a solution. So you can see how the solution would look like if the ball is bouncing on a surface starting from some 10-meter height. We are throwing it up towards some 22 meters high and then bouncing it back. So I hope this makes sense to you. If you're interested, and if it looks like it's if it looks exciting, do let me know. There are many things that you can do to learn Simulink. When you open up Simulink by doing this, let me show you. Let me just move certain of the things out here. So out here, when you open MATLAB, you will see there is, under the home tab, there is Simulink button. You can access Simulink from that, or you can also type Simulink in the command window and you will be able to open up this particular page, which is known as Simulink start page. In start page, on the left side, you will see the recent files, and on the bottom, you will see there are some learning modules for you. So it has Simulink, Simscape, other things. So Simscape is another entity which is a part of Simulink. I'll show you that once we talk about biped robot. So you can use these material to get started. I believe Shavik mentioned that to you in the first part of this first session itself, right? Great. Now with that brief introduction, let me actually take you back to our biped robot project and show you what I have built. Okay. So what I did is, because our biped robot is a dynamic system, walking of that is a dynamic process itself, I created my biped robot in Simulink. And I'll tell you a couple of reasons on why I did that. Okay. So if you notice here, there are multiple things that would look very much alarming to you in the first case, but don't worry. This is just because, this might be first time you have seen Simulink. If not, you might be quite familiar with this, right? So there are three aspects to this. First thing is our environment. That was the first step in our RL workflow, right? So let's take a look at our environment. In this case, our environment is a walking robot, right? So here it is. So if you see, the walking robot gets some input and it's actually sending out sensor measurements out as an output. So let's take a look at how we have built our robot in here, right? So what we can see out here is there is something: robot left leg, robot right leg, the world and the ground, the sensors, etc. So let me actually go to the right leg and see what it is. So right leg consists of hip joint, knee joint, ankle joint, lower leg, upper leg. So what it is actually doing is, let me show you what it actually does. So if I go inside this block, what you will see is these are just some physical blocks, right? Some physical entities like joints. This is revolute joint. So revolute joint actually allows you to change that angle, right? There are solids, some solids that are connected to the revolute joint. The solid is cylindrical in nature. Similarly, there is a knee joint. Then there is a hip joint, right? And there is, upper leg. And then there is foot. The foot looks something like this, which is flat foot, right? So the whole idea that I want to showcase out here is this entities that you're seeing right now is a part of something known as Simscape. Simscape lets you work with physical, blocks or physical units. The whole idea is you do not have to work with equations. Now, rather than equations, you're connecting solids, right? In this is Simscape multi-body. So you can collect solids like solid joints, solid body, flexible body, contact forces. And what Simscape does is, at the back end, it automatically creates equations for you to help you expedite your work quite fast. So just to show you certain examples that might be of interest, let me show you one so that we can actually get started with our real requirement, right? For example, this is an example of, okay, rather than this example, let me show you this. So this is an example of a robotic arm manipulator, which is modeled in Simscape. So you can see how it has been modeled in Simscape. If I run this, it will, what it is doing is it is trying to convert the physical files, which is the physical blocks, into mathematical equations and then running it. So if you see, it is automatically animating the entire dynamics of what I have put up, and it is showcasing me that dynamics in real time. Right? And the beauty is you can actually zoom it in and actually take a look at different angles of this. Okay. You can see how different things are working in different scenarios. Let me loop this so that we are able to see this in different angles. Okay. So if you see how the joints are moving, you can actually figure that out. So this is quite intriguing when it comes to, looking at different aspects of your solid body moving, right? And the structure of this particular robot arm is actually taken from something known as CAD. So we have taken CAD model for this. Okay, great. Just that's an introduction of this. Now let me get back to our presentation to show you what's happening. So the environment we have created in Simulink, we have seen that already, which is made out of all these different blocks. Now comes the rewards, right? The second portion is rewards. So what we did out here is, so in our walking, biped robot model, we had this as our environment. The reward was something that we created based on a paper, which was by, which is given up over here, emergence of locomotion behaviors of enriched environmentals. So the reason is because we understand that reward formulation is very critical when it comes to reinforcement learning, because if your reward formulation is right, your agent is going to learn the correct thing. Otherwise, your agent is not going to learn the correct thing to do, right? Just to walk you through a very simple reward that we have set up over here. We are rewarding the robot for going in the X direction. So V of X corresponds to the velocity in X direction. We are giving a positive reward to it, which is multiplied by 1 as forward reward. If it is deviating in the Y direction, right? If it is deviating away from the straight line, then we are penalizing it, and we are penalizing it very heavily, like 3 times for deviating. We are penalizing it for falling down because we want it to actually be stable and walking, right? So the Z value is actually the Z direction displacement, and we are actually penalizing it heavily for falling down, right? You can see 50 times we are we are penalizing it. Now we are also penalizing it for not for taking extra torque in the joint. Like it should not suddenly, in a jerk motion, it should not go from one position to another, right? It's not physically possible. It should be slow enough. It should be reasonable enough, and it should be realistic enough. So we are giving penalty for that, right? That means negative, negative reward. Finally, if it is able to walk for a longer duration, or if it is able to sustain the, upright motion for a longer duration, we are rewarding it for the duration itself, right? Is this clear to everyone, or any questions in this? Shrikant, this would work in versions anything above 19, if I'm not wrong. If you have any challenges in working with the latest version, please do let us know. We'll try to work it out and ensure that you're able to work with the latest version. So in this reward formation, is any doubts in this? I know you may not be familiar with Simulink or Simscape right now. Please don't worry about those. These are just tools that we are deploying to work or solve our problems. If you feel that these tools are easy and for convenient enough for you to work with, then I have shared certain resources with you. You can also reach out to us, and I'll be happy to work with you on to enabling you to set up your problem statements. Okay. For now, our focus is looking at how we are actually putting all the things that we have studied till now, or we have understood till now, in a software world, because obviously we want the machine to learn, right? And if it could learn by just us saying, that'd be awesome. But unfortunately, it does not do that. We have to code it in a proper format to get the things moving across, right? So it is very useful if a lot of coding things can be simplified, because we may not be expert in programming, but at the same time, we are experts in our own domains and we are excited to use these technologies for us, right? So we want to enable that for you. So I hope this reward formation is clear to everyone. Reward for going forward, reward for sustaining that forward motion and upright motion, penalty for deviating from the straight line, penalty for falling down, penalty for sudden jerk movements. Okay. So these are the two aspects of reward, environment and reward right now. Now let's go to the network design, actor and critic network design, right? So let me actually introduce you to certain other things. So this example file, if you see, this is a MATLAB script. Script is something wherein you have a collection of MATLAB codes to work with. Okay. So in the script, let me run the script a little bit. What you see is, this is a live script which allows us to put up all the documentation and put images and everything so that it is easy for us to understand. What we are doing first is, we are saying, hey, this is the parameters of the robot, like the length of the leg, the area of the leg, the shape of the leg, etc. Right? This is the environment where we have created this particular robot, wherein our environment is located. We are opening the model where the environment is located. That's it. Here, what we are trying to do is, we are trying to create an environment first. We are connecting the environment to the agent, because agent is something that should understand where the environment is, right? So in MATLAB, we are creating a description of our process itself. We are saying, hey, number of observations that I'm going to make, or the number of states I'm going to look at, is 29. It is going to be a continuous state, because we are working with continuous entities, right? Joint angles and everything is continuous. And these are observations. And we are saying there are 6 actions you have to take, 3 joints each leg, so 6 joints in total. So you have to take 6 actions, correct? Now, where is the environment located? We are putting that information out here. Please do not mind if you're not able to follow. Just qualitatively, let's see how we have broken down this problem into set of actions, so that no matter which software or which language that you work with, these are the similar kind of steps that you have to work with, right? You will have to break down the problem into smaller sections and then put it forward. Then you have to define the reward signal, which we have already done in our Simulink. Then we have to set up the policy. And policy is basically, we are going to use neural networks, actor and critic technique for putting our policy out. So for actor network, we are using something known as deep neural network to create our neural network. So let me show you where deep neural network resides. In your MATLAB, there are some applications which helps you to interactively create your models. So out here, one of these applications is Deep Network Designer, which gives you flexibility on creating your neural networks in a very interactive format. Okay, so you can, similar to Simulink, you can drag and drop certain layers and blocks and etc. That will help you to create your neural network in a very quick fashion. While it's turning on, let me show you the video. So you will see this is actor network that I was creating. On the left, you will see there are these layers that I can use. And what I do is I just drag and drop and put these layers in this window and then actually get it done. So I think my Deep Network Designer is turning on. So while it's turning on, let me show you the video back again. So you will see these layers I have dragged and dropped it into the canvas and connected them. I can also interactively change the parameters needed be. And then once I have done creating my network, I can easily create a code out of it so that I can replicate this as and when I go ahead. Okay, I think my Deep Network Designer is open. So you can also use some pre-trained networks if you are trying to experiment with transfer learning of some sort, which is, I'm not going to leak out. So I'm not going to say further much on that, but if you're interested, to let me know. So you will see that these are the layers that I can, just drag and drop, connect it, analyze whether I am doing the right thing, if the parameters are, set properly or not. And then based on my understanding, what I can do is I can actually export this into a code or into a model itself. So this saves a lot of time, to be very honest, for me, because most of these things, if I have to code, it will take a lot of code lines to actually put it across, which I'm comfortable to do, but this is a little bit more, efficient for me because I can play out with different branchings and other things. For example, if I have 2 different branches and I have to connect it all together, then I don't have to worry about a lot of things, right? I can actually do that quite effectively by just clicking, dragging and dropping and all that sort of things. Yeah, I have to put a addition block out here, right? So I don't have to kind of worry about different things not working and etc. And I can be as messy, and then it will auto arrange for me and get things moving across. So yeah, that's one thing. So in this way, you can actually create your own, actor and critic network. And once you export it in terms of code, you will see these are the lines of codes that you may have to put up even for a simple network that we created just now, correct? Similarly for critic, we create one. Now the agent, right? The agent is actually a block in our Simulink model. So this block is actually taking 3 inputs. One is, what are the observations that can be made from the environment? What are the rewards that it can expect? And when do you think the simulation should stop? The boundary conditions, right? So these define the boundary conditions of our problem statement. This is quite important if you're working with something which do not have episodic episodic nature, if it is something which works for infinite amount of time, etc. Okay, great. With that in mind, let me go back. Now let me show you one small thing. So once you have created your network, you have put up optimization, whatever gradient optimizer, Adams optimizer that you have worked with. What are the parameters? The learning parameter, the regularization parameter, the threshold, etc., etc. So these are the parameters that you set up for, right? Last but not the least, you have to connect these actors and critic together as a part of your agent, correct? And your agent is going to be a deep deterministic policy gradient agent, okay, wherein your policy is going to be your actor and the reinforcement learning or updating portion is going to be your critic, and the combination of that is going to be your agent, right? And that's what we are going to present out here. And the DDPG agent has an actor and a critic that we have defined in terms of neural network as its actor and critic network. Okay. I have also shown an example below by using a different kind of agent, just in case if you're wondering, is there only actor and critic that we can work with? You can also take a look at different kind of agents and how the simulation works. Okay. So let me quickly try to see if I can run this, because I have to kind of get rolling here. Let's see if I'm able to show you a video of how it looks like. So I have saved this RL agent in this mat file. So if you're interested, you can actually load it and run it at your end. Yeah, I think I can show you this. You can see how the agent might look like initially. So we are at this particular range right now. Let's see. Yes, you will see this is the trained agent that I have worked with. You will see how it is working, right? How it is working. So let me actually put it in perspective. So let me kind of move it around so that we are able to see it properly. I hope this is visible to everyone. So you will see how this is moving across, right? So this is the final simulation after training, right? So if you feel like this is not enough, you can retrain the system and get it moving across. Okay, great. With that in mind, let me actually head back to our presentation. So the whole idea is, initially when you start training, it will look something like this. Your robot will immediately fall down. Even before taking a small step, it will fall down. Then slowly and gradually, what you will see is it is able to take some distance forward, maybe a step or two forward, and then fall down, right? Now, eventually, you will see it is able to maintain the upright position for longer time, but it is not able to follow the straight line. So if you notice, this is all the game of rewards. The reward was maximum negative for falling down. So it is first learning to stand straight. Then the reward was negative for, positive for, not positive for sustaining the walk and in the and moving in the X direction. So it is able to move in the X, it is able to sustain the walk. Then it was being penalized for deviating from X axis, right? Deviating in the Y axis. And that is how it is able to, walk in the correct direction now. So it all depends on the kind of reward that you have set up. If your reward was primarily focused on not deviating, then there is a possibility it would have never learned to walk up properly in the first place. So you have to prioritize things. First, we have to learn to make it stand. Then we have to make it move forward, right? It should take steps. Then we should focus on sustaining that forward motion. Then we should focus on ensuring that the path is correct, right? So that is the priority that we are giving. I hope that makes sense to everyone, right? So in order to scale up this process of training, you can always use parallelisms that are available inherently in MATLAB, which is what we use. And it was quite fast for us to work with this. Okay, you can also use your GPUs if needed be. And the beauty is, finally, as I showed you, the robot was walking something like this, and it was quite an accomplishment for us, because this was something first that we did for reinforcement learning, and it was quite nice. And this actually led to a lot many robots or robotic teams actually working with reinforcement learning to interactively teach or make their robots come to life. Okay. So just to wind up, there are many different application references that are available in MathWorks documentation if you're interested in working with reinforcement learning for any kind of problem statement, whether it is robotics, whether it is lane keeping, whether it is chemical engineering. If you do not find an example, please do not fret. Reach out to us at any point of time. We'll be more than happy to actually work with you and get you the required results. There are some pros and cons of reinforcement learning that we should all be addressing. I think most of it we have observed as we move ahead, but we should definitely highlight it, right? So the major pros is you do not require to collect all the data prior to training, because the data is coming from the interaction with the environment or interaction data, right? So you can work with that. So it actually gives you a lot many flexibility in terms of the hardware resources that you need. Second is, thanks to the deep neural networks and the possibility of working with these deep neural networks, we are able to actually solve complex end-to-end solutions and hard to solve problems using those. And even uncertain nonlinear environments that we earlier were not able to use in its entirety can be used now, right? There are definite cons. Trained policies, we understand that if we are to put it in real world, there might be certain problems or cases where it is hard to verify. How do we do that, right? So we cannot promise any performance guarantees. Many trials and samples are required, even though if we are using actor and critic, it's still a lot of computation to work with, right? And one thing I want to highlight for everyone, if you're planning to work with reinforcement learning, do ensure you do not start with real life hardware right away. Some people will believe that, why do I need an environment and simulation environment? I can directly connect with real life hardware and let the system learn from working with the real life hardware. It sounds lucrative, it is possible, but it is dangerous. So before you do that, you have to ensure that you are setting up all the fail safes. And if you damage a real world hardware, it is too expensive and it may also put you in risk. So be very careful when you're working with real life hardware for training purposes. Okay, it is easily possible that you can do with your real world hardware because you do not need an environment, but at the same time it is also very dangerous. I'm highlighting that again. Okay, lastly, a lot of design parameters have come up, right? We have to talk about reward signals. What are the parameters, what rewards we need to put up? We have to talk about network architectures. What are the parameters we require for training these networks, ensuring that the process is actually quite robust and etc. So there are so many parameters that we have to consider, right? One thing we know for sure is simulations are the key for reinforcement learning, right? So is there a way we can help you out? So we have tried to put certain things for you so that if not elevate this completely, we are able to help you out in some context. There are many existing codes and models for environments that you can utilize. If you believe that you are working in a particular area and you do not have an environment for you, first of all, try out in the documentation. If you're not able to find it out there, do let us know. We most probably might have an internal team who is working on something similar, and we'll be very, very happy to share, what models and existing codes that we have so that your work can be expedited, right? Second is, if you're using simulations as your environment, then what happens is you can actually simulate for extreme conditions, right? If, for example, if you are working on automated driving cars, then using simulations, you can actually simulate US traffic, you can simulate Indian traffic, you can simulate traffic which can be even on Mars at one point of day, right? So the whole idea is you are able to simulate extreme scenarios which may not be even possible, but if your policy is working better, that means your policy is robust, right? So that you can get the tag of my policy is actually completely trained now. Then in order to help you quickly do your multiple trials and simulations, one thing we can help you out with is running the simulations on parallel so that it accelerates your process quite fast. And for design parameters, I think examples are the first case scenarios we can help with. And one place that I always find help in is research articles. Quite often than not, the research articles are really a good place to start with when it comes to parameters. And because we all are researchers out here, we understand that, yes, this is one thing that we can always do, right? If you do not find one, do let us know. We also work with many, many industries. So if there are any parameters we believe it would be helpful for you, we'll work with you to figure out if we can find some, average parameters to share with you. So at the end of today, I think these are the key takeaways that I wanted you to have. One is, what is reinforcement learning and why should you care about it? I hope this is clear to you, because this is quite robust and useful even in situations where typical or traditional controls and systems will not work. Second is, I think you should be more comfortable with what are the different elements, what are the different verticals that are a part of reinforcement learning workflow. How can you set up certain things? What are the things you should keep in mind while you're working with reinforcement learning? And also to understand certain drawbacks and benefits of reinforcement learning, right? I hope these are the key takeaways that you have successfully identified during this session. Please do let us know, what do you believe? If this was something that, we were able to add value to what you wanted to learn about reinforcement learning. Were you able to get a, more confidence when it comes to reinforcement learning? Do let us know in the feedback form. I believe Pranav would have shared the feedback form in the chat window. There are many, many other things in reinforcement learning that we can actually talk about. In case if you have any particular thing that you want to discuss, please reach out to us. Pranav and Shavik will share our email IDs in the chat window if you need it, if you need to, reach out to us. Also, we have your email IDs that you will be using to fill the feedback form. So we'll also share these resources with you and also connect with you separately. So I hope you had a wonderful day and learning of full of reinforcement learning. For more resources, there are many resources that are there in MathWorks website and Tech Talks. And some stories for your inference, like these are from Atlas robot by Boston Robotics that you can actually take a look at. How this biped robot is actually working quite well and moving across in different atmospheres. And you might have seen this dancing robots by Boston Robotics some time back. So do take a look at these videos. You will be quite excited if you're working in robotics environment. If you're working in any other environment like MNG or anything, please do not hesitate. These are equally applicable to your area of expertise too. So thank you and have a great day, everyone. I hope you had a robotic day with a fun robot, and hope you have a fantastic day ahead and fantastic conference to continue with. So I think we can wait for some questions if we have time. I'm not quite sure with the time.
Yeah, thanks, Akhil. I think we are on time because there is another session starting up.
Great.
Great. Anything else? Any other questions? I think the questions has been more or less, yeah, it has been covered while we have been proceeding. In terms of release, yeah, so it's Akhil was showing in the latest release, but it was there for the last couple of releases, I believe.
Yeah,
to a version
it's there since 2019.
2019. Okay, great. So yeah, 2017, Srikanth, we won't be probably finding reinforcement learning, so that came in 2019. Any other questions?
I don't see any.
Later on, if you have any questions, please fill out the feedback form that Pranav has shared, and also feel free to reach out to us any point of time later on if you have questions.
Thank you everyone for participating. It was great interacting with all. I hope we stay in touch and we are able to discuss further, and I hope we are able to work together in certain projects. Have a very good evening, everyone. Have a good day. Thank you so much once again.
Thank you, Akhil. Thanks, Pranav. Thanks to all the participants and organizers.
Thank you. Thanks, everyone.
Thank you, sir. And also thanks to Pranav and Akhil. So we are ending this session here. Now our next, we have 2 sessions running in parallel. One is on data-driven modeling and fault detection using principal component analysis and its new variants. And another one is on a priori identifiability of chemical, biochemical, and biological networks. Okay, thanks.